we want to prove all this here, and essentially the only thing we have to prove is the first statement. So let's look what's written here. We have a unitary representation and on V, and there's an invariant subspace U. And now what we want to show is that the orthogonal complement U perp is also invariant. And if we have that, then the rest follows automatically. So V is U plus U perp, direct sum. If both are invariant, then each of them carries a representation again, call them gamma 1 and gamma 2. And then the original representation, gamma, which lived on V, is equivalent to the direct sum of the two representations, which are carried by U and U perp. And we simply write this in this way. So this equal here for representations essentially means equivalent. Okay, and if we have that, then we also have Maschke automatically down here. So just take any unitary representation, finite dimensional, and it's automatically a sum of irreps. So why is that? We just start with the carrier space. If there is no invariant subspace, then it's irreducible and we're done. If we find an invariant subspace, say U, then we know that U perp is also invariant. And now we repeat. Now we check for each of these whether they are irreducible or whether there is an invariant subspace. And if there is an invariant subspace, then we split it up in something plus the orthogonal complement, and we do this until there are no more invariant subspaces. So the only thing we have to prove now is statement 1 in the theorem. Let's take a vector U in the subspace U and say a vector V in the orthogonal complement. And now let's look at gamma of G times V, scalar product with U. So what we have to show is that this is 0, because this one here is in U perp, and if this is still in U perp here after multiplying with any gamma of G, then we see that U perp is invariant. So how do we do this? We pull the gamma of G to the other side. This gives gamma of G dagger times U. Now we use that the representation is unitary. So gamma of G dagger is gamma of G inverse. And now we use that it's actually a representation. So we have gamma of G inverse times U. Okay, so here we used that it's a unitary representation, and here we used that it's a representation at all. And now we're done, because this here is still in our subspace U. It's invariant. We just applied the representation matrix here, and now we have a scalar product of something in U perp and something in U, so it's 0, and this shows that this one here is in U perp.